All right, here is our first example of an equilibrium problem. So we have our sign. It has a weight of 215 newtons. It's supported by a beam that, when it says a uniform 135 Newton beam, the beam itself is uniform material, so we can say that that force of gravity, the weight of the beam itself, acts as if it were only in the middle. Again, that goes back to center of mass and just making it a bit easier to talk about the force of gravity. We want to find the tension in the wire connecting the beam to the wall. So again, we need to draw a free body diagram, and we need to do that for the object that connects everything together, which in this case is going to be the beam, right? The beam is connected to the wall. Both over here, there's a pin of some sort connecting it to the wall. There's a cable. That's where we're trying to find the tension. So I guess they call it a wire. There's this sign. So we need to draw the free body diagram of the beam itself. And where we draw the forces is important because we need to account for torque. We know the net force must be 0 in both the x and y direction. We know the net torque must be 0 around any rotation axis. And again, that's just because of what we're defining as equilibrium, and because we don't want this beam to go anywhere. We want it to hold the sign up. We don't want cables to break. We don't want it to start rotating. So the net torque needs to be 0. And torque depends upon the lever arm, how far away from a rotation axis, and then the perpendicular component of the force. We can also write this as RF sine phi. Oops, sorry. All right, so our beam. I know the sign is hanging at this end. The weight of the sign is 215 newtons. That's given in the problem. Since everything is at rest, this cable that attaches this sign to the beam has to equal the weight of the sign, otherwise there would be acceleration. So we can go ahead and say that the sign itself is exerting a force of 215 newtons downwards on the beam. The weight of the beam itself, because this problem tells us it's a uniform beam, we can say that the force of gravity on the beam, its own weight, acts exactly in the center. So that's where I'm going to draw it. 135 newtons, the weight of the beam itself, in the exact center. And that's because that's where the center of mass is located. We have our wire, the wire right here. We're looking for the amount of tension in this wire. So I'm just going to call it T, representing the force. Now that's not all the forces. The beam itself is attached to the wall. So where I drew this big circle, I know there's some sort of force X from the wall. So I'm just calling it Fx. There's going to be some y component of force as well. Whether it's up or down, I'm not necessarily sure. So I'm just going to go ahead and draw it upwards. And again, my math, if I calculate for it, my math will give that to me. All right, so let's see. I think we have accounted for all of the forces this beam would be experiencing. Now, as far as answering this specific question, I'm going to choose the rotation axis. So again, for torque, we need to define a rotation axis. I'm going to put that at the left end of the beam where Fx and Fy from that pin are acting. The reason why I'm putting it there is the torque would be 0 for both of these because R is 0. Any force that acts at the rotation axis is not going to produce a torque. It's not going to produce rotation. So again, if you try to walk up to your door and push on the hinges, that's essentially what we're saying. Trying to push on the hinges, I'm not going to make the door rotate. So similarly, if I put my rotation axis at that left end, those two forces, because they act right there on the rotation axis, they will not cause any sort of rotation. And so that really is just a matter of simplifying my equation. This comes from practice, which is why I'm just telling you to go ahead and choose your rotation axis in equilibrium problems to be where you have unknown forces. Now, technically, that definition, I could put the rotation axis down here where tension is applied, but then there would be a torque created by the y component of the force from the pin. So it does take practice. If you end up taking statics, you'll get lots of practice with this. As far as continuing with our problem, we will need to calculate the torque due to the tension force, the torque due to the 135 newtons, the weight of the beam itself, the torque due to the 215 newtons. All of those added together need to add up to be 0, right? The torque due to the x and y components from the pin are 0, so I'm not including those in my equation. Now we could, if we want, we might recognize that the tension force, the torque it would produce would be counterclockwise, whereas the torque due to both of these weights would be clockwise. So magnitude-wise, the torque due to tension has to balance out the torque due to the 135 and the 215 newtons. Now, that doesn't mean those forces balance out, because that's not the case. We'll write out the force equations after the torque just so you can see them and have the practice with them. But let's go ahead and look at the torque now due to these tension, the 135 newtons, the 215 newtons, and plug them in. So the torque due to tension. The lever arm points from the rotation axis out to where the force is applied. So from the left end of the beam over to where the cable is attached. If I come over to the original picture, they're showing me that that is the 135 newtons, or sorry, 1.35 meters. So torque due to tension is going to be 1.35 meters, that's the R. We have the force of tension, but that's not perpendicular, right? It's not perpendicular to the lever arm. This tension force has a Y component and an X component. It is only this Y component that is contributing to the torque. Now I can totally draw that over here as far as my components are concerned. My Y component of tension, let me erase my counterclockwise. That Y component of tension will be the overall tension times the sine of that angle, the 35 degrees in here that they give us in the picture. So that goes back to our just general force vectors. We can find components of a force, x and y components, based off of the little triangle we draw. Now again, notice what we just wrote, RF sine phi. That's what we have right here. R, the force is T, sine phi 35 degrees is the angle between R and F. I like to think of these things conceptually as well, rather than just trying to throw numbers into an equation, because this phi has to be the angle between R and F, which may or may not be the angle that is shown in the problem. So we just want to be careful about writing out and choosing angles in that equation. All right, so that's my torque due to the force of tension. I need to find the torque due to the weight of the beam itself and the torque due to the weight of the sign. So the torque here due to the 135 newtons. Lever arm starts at the rotation axis and points towards over to where this force is applied. So the R for this 135 newtons is going to be half of the entire length. So the 1.7 meters. Now that goes back again, they told us this is a uniform beam, meaning the center of mass is in its center. And that's where we can draw the force of gravity as if it were acting at only one location. So that is the R. The F, the force is 135 newtons. Now, the angle between these already is 90 degrees. So we have, coming back to our equation on the right, we have the lever arm and the perpendicular component of the force. So technically the angle between them is 90, so sine of 90 is 1. So I'm going to put this in for the torque due to the 135 newtons. So we have R times F, and specifically the perpendicular component of F. All right, so to finish out net torque, we need the torque due to the 215 newtons as well. So the torque due to this guy, the sign at the end, R always starts at the rotation axis and points out to where the force is applied. So it's kind of hard to see. I started the lever arm at the left where the rotation axis is, where I drew that, and drew it all the way down the beam to the right end, because that's where this force from this sign is located. So this R is the entire length of the beam. We need to multiply that by the force that's already in newtons, so that is the force. And the angle between these is 90 degrees, so this is a perpendicular component of force. So this is what we need to add to our equation on the right. Add the 1.7 times 215. So this equation is our net torque equaling 0 equation. And if you notice, T is the only unknown. This is why, just because of my experience of solving problems, I know if I put my rotation axis where I have unknown forces, that sometimes the torque equation will allow me to solve for the unknown I want. That's not always the case, but typically, from my experience, I start with my net torque equation, and then if I don't have enough, I go back and write out my force equations. Here, I have everything I need, so I'm going to plug the numbers in to calculate this tension force. I'm getting 620 newtons as my tension force. And so I'm done. That's what the problem asked me to find, is the tension in the wire. Now, I do want to write out the force equations just for practice, because it's totally possible the problem would ask you the force from the pin, for example. To relate everything else, I could technically calculate the torque around a different rotation axis. That's valid. But I know also in equilibrium that the net force in the x direction must be 0. The net force in the y direction must be 0. So let's write out the equations representing that. In the x direction, it's kind of covered up now. I drew the x component from the pin, the x component of its force to the right. Tension has an x component that points to the left. So those are the only x components. They would need to add up to be 0. The x component of the force from the pin would be the x component of the tension force, but that would be the tension force times the cosine of that 35 degrees. We now have the tension force. I'm going to slide this up a little bit. So we can say the x component, the force of the pin exerts, would be 620 times the cosine of 35. And since we're getting a positive answer, that means I drew it to the right. That means to the right is the correct direction. So that would be the x component of the force the pin exerts on the beam. In the y direction, I drew the y component of the force of the pin upwards, because I wasn't entirely positive. The mathematics will show us if I was right or not. So the pin I drew as an upward force. The tension we know has an upward y component of force. The 135 newtons points down. The 215 newtons points down. Those are all the y components of force. So those need to add up to be 0. So this portion of solving a problem is just rewinding back to like chapter 6. Just those components, x and y direction. So let's see. When I bring everything to the other side, oops, 215 minus, so ty we know is t sine 35. I'm going to go ahead and plug that in. Let's see what we get. All right, I'm getting negative 5.74. It's a small force. The negative sign means I drew it in the wrong direction. So this y component of force actually points downwards. And so the pin's force points 508 newtons in the x direction and down just this itty bitty 5.74 newtons. This is what the force of the pin looks like. And we could find magnitude and direction just like we did before, but I'm not going to take the time to do that. I think we're good at this point.